Thank you very much. It's always a pleasure for me to be in California since the first time. The first time was in your institution, but before you arrived, probably, at Irvine. A short period of 3 months. The rest of the time I was in New Jersey. So these lectures are going to be a bit different because in the first part you are going to think that this is an history of science seminar. At the end, I hope you will change your mind. Okay, I'm going to advocate the idea that at the very beginning of quantum mechanics, it was neither the Hamiltonian viewpoint nor the Lagrangian one, nor the Poissonian one, which was crucial, but Hamilton-Jacobi theory. So I'm going to extend a result of Jacobi about his Hamilton-Jacobi equation in the case where you have noise. We all know that in the last 10 years or so, Hamilton-Jacobi-Bellman become even more important for some people because, for example, it happens in deep learning and many other fields. So what is the relation between those two equations? In what way Hamilton-Jacobi-Bellman is a natural extension of the classical theory? Okay, for us, I mean somewhere between probability, physics, and mathematics, the difficulty in this connection between classical and Hamilton-Jacobi equation is that, of course, according to Feynman, we know that quantum trajectory should be extremely rough, and you need to regularize a number of principles of classical mechanics, of course, starting with the least action principle. So all what I'm going to describe is founded on an idea of Schrödinger in 31-32. So he just, quantum theory as we know it was almost concluded in some sense, and he already started to criticize the theory without pity, you know. He was very brutal, and he didn't like especially the role of probability, the interpretation of probability in quantum theory. So he designed a problem of classical statistical physics. But as you will see, very curiously close in structure, at least algebraically, from the theory he just contributed to create. So the result will be, he expressed this problem in variational terms, and we know today for a long time what are the solutions, in the sense what are the critical points of some functional that I will describe. But his real purpose was the probabilistic foundation of quantum mechanics, if any. Because in the simple case, pure state, in those days, this is still as mysterious as at the time of Schrödinger. So I will also argue that Hamilton-Jacobi-Bellman has really a dynamical role, which is at the center of the strategy that we are going to adopt. Here is my summary. A first comment about the classical Hamilton-Jacobi and the relation with quantum mechanics. The first paper of Schrödinger, 26. Then I will jump 6 years, and in 32, we started to design this analogy. I will also describe Theorem of Jacobi, which is not very well known. Personally, I didn't know it, actually. Jacobi, as you know, suggested the creation of a vision of mechanics founded on a nonlinear PDE. So he was immediately criticized by people in Hamiltonian mechanics and Lagrangian mechanics, because in some cases, at least, for example, for quadratic Hamiltonian, you can solve the system, and the equation of Hamilton-Jacobi-Bellman, Hamilton-Jacobi is always nonlinear. So he had to answer to criticism, and he designed an integrability theorem for his equation. And in some sense, the summary of what I'm going to say is that following exactly the same strategy, modulo, taking into account the rough trajectory that we are dealing with, you can have an integrability theorem for Hamilton-Jacobi-Bellman. So it's very simple. H bar going to 0, you are back to Hamilton-Jacobi. So the second point I will describe is integration method for classical Hamiltonian system. The third one, stochastic geometric mechanics on a Riemannian manifold. And finally, the last one, the extension of Jacobi integrability theorem. Okay, here is this little graffiti. This is because I have a new iPad and I try to use it for the first time. So it's a bit ugly, don't worry too much. Okay, in 26, Schrödinger wrote his equation, and he had to start from, curiously, Hamilton-Jacobi equation. The star will be a real star field S star. You will understand why I take this notation, but everything will be real in this talk. H is the classical Hamiltonian, and it is a Cauchy problem. Something that we forget, at least I never heard this, there is an adjoint Hamilton-Jacobi equation, which is this one. You don't mind generally in classical mechanics, because in classical mechanics you are looking for smooth trajectories. As you will see, the adjoint Hamilton-Jacobi, this pair of Hamilton-Jacobi equation will be useful and will have a key role in the interpretation of what we do. Okay, one way to interpret the second one is that it is a time reversal of the first one. Precious in my perspective and in the one of Schrödinger. Okay, so the equation for S in classical dynamical stochastic control, classical optimal control, I mean, is called a dynamic programming equation for a given cost, which for any physicist is just a Lagrangian. Okay? So let's come back to the simplest of all the Hamilton-Jacobi equation, which is this one. Yes. Sorry, this is a bit strange, but okay. In 1926, when he wrote the first paper on his equation, he did a very interesting change of variable, a logarithmic change of variable in the classical Hamilton equation. So it means the whole of the moment is a logarithmic derivation. Okay, he didn't try to solve this new equation in terms of psi, but he looked for an equation, a PDE for psi, solving some kind of variational problem. The problem is not particularly interesting. And the conclusion, we know it. This is this one. And so since then, to get rid of this, since then we called capital H a quantization of the classical Hamiltonian. From now on, I will do like Feynman, take the simplest class possible, the one which has classical counterpart, so the intuition is better about what we are doing. A little time after Schrödinger, I guess, Dirac was advocating a version of quantum theory founded on Poisson bracket, made his important remark that if you want to compute something about the evolution between a configuration Q0 and Qt, a term like this should be essential. Okay? And we all know that what Feynman did with this observation. This is the origin of his PhD. You have to exponentiate the action associated with the Lagrangian hell. Here, there is something that he looked like as a measure, which is not, but okay. And he considered a set of trajectories ending all at the time t in the future to a given point. This is a Lagrangian path integral. Note that when the paths are smooth, classical, the Lagrangian has this form for in our case. So as we all know those days, the d omega, this kind of flat measure, does not exist. And the usual way to get rid of these difficulties is to say, okay, we are going to be Euclidean, to replace t by it. And then we know that there is a Wiener process. So it's the same image. You consider only the path reaching the position q at the time t. And you have a representation, a probabilistic representation, which involves v, and which is associated with T's PDE, which is a heat equation with an initial condition, Cauchy problem. But note that in this sense, you have some change of sign in the Lagrangian. And it is still true that the derivative of the paths are divergent, of course. It doesn't make sense because the Wiener paths are extremely bad. Note the change of sign of the potential, which is normal. Think about Newton equation when you replace t by it. Okay, so the interpretation of T's formula, which is called generally Feynman-Katz formula, is that you are in statistical physics. The potential V is interpreted as a killing rate, which for any physicist is awful. But okay, this is a probabilistic interpretation. And of course, the PDE is the heat equation, essentially. So it is a paradigm of irreversible evolution. Okay. Now, Jacobi integrability theorem. Here, I'm going to use the terminology of Jacinta Hildebrandt, the second volume of the massive book on the mechanics, calculus of variation, more precisely. So, Jacobi was faced with the challenge to solve Hamiltonian equations, which were already very famous, using his PDE. So here is what he does. Instead to consider one equation, he considers a bundle of equations. A solution depending of a number of parameters. So a bundle of trajectories. And he called a complete solution of his equation, one which, suppose that Q is in Rn, then as many real parameters than the configuration space. He calls this solution complete. This is his terminology. If the two conditions are satisfied, S is smooth, here it will not be the problem. The determinant of the first point here, E, is non-zero in a domain of the extended configuration space. And also, you need a good domain for the parameter. The key point is that for any value of the parameter in the appropriate domain, S star for any alpha solve Hamilton-Jacobi. So it is a bundle of solutions. Then the idea of Jacobi is using these conditions, his idea of complete solution is going to build a family of two-parameter collection of the Hamilton canonical equation. Here is his theorem. Suppose that H is ST is complete, and you have Q and P depending on alpha and beta to a family of n parameters each. So the first observation is that the derivative of S star with respect to the first family of parameters, alpha, give an order family of parameters. The right-hand side is a constant. Actually, it is the key point of his method. Then P will be the gradient of this object after substitution of the Q. Indeed, the conclusion is that this family here is a 2n parameter family of the solution of the Hamiltonian system. This is his way to show that he can solve Hamiltonian equation using only his nonlinear PDE. Of course, here I don't, it's not necessary to think about the second, the adjoint Hamilton-Jacobi equation, because everything is supposed to be smooth. For those who are interested to this, an observation, a complete solution of Hamilton-Jacobi does not imply complete Liouville integrability. Since the work of Arnold in the 70s, 80s, Liouville integrability is supposed to be the official, the best method. So there are sophisticated and non-trivial relations between the different concepts of integrability. Okay. So now I'm going to give you the main result that I need to have this extension of Jacobi integrability theorem. Suppose that you have a classical Lagrangian, L0, and a diffusion evaluated in M. Most of the time, Rn will be sufficient. Then you define this conditioned expectation. You integrate L0, but, you have to be careful with this guy, because of course normally it is on a diffusion process, it will be divergent. So the right way to do this is to have a sum of two terms. One, which is the I component of what we call the drift. The second one is a purely geometrical term due to the fact that we are working now on a Riemannian manifold with a Levy connection, Shirita connection. And the second term is the one related with the metric diffusion term. So this object is well known except for the, let's say, the geometrical content. It has been around in stochastic control theory since, I don't know, at least the 60s. The important point is that when we do this, we regularize the key divergent object along nasty trajectories. No, the good news is that it's relatively easy to find what is the diffusion. Remember the metric E6 here. The diffusion would solve, how can you characterize a diffusion in the whole family that you consider? Typically, you don't even impose the family to be Markovian, for example. The drift, a priori, could depend on the past. So there is a theorem, stochastic Lagrange equation, which take this expression, which looks a bit complicated, but in coordinate, it's the usual one, except for a few details. Each time you have a derivative, you have to take the one involving the extra term of geometrical origin, due to Ito, in fact. And this one, because you are deriving a one form, you need an expression like this, which is called, those days, which can be called a second order Lie derivative or time derivative. Here I use a reference to a work of Meyer and Schwarz in the 80s that personally escaped me completely at the time, but as is very interesting. A second order geometry. Why second order? Well, you see why here. When h bar equals 0, you are in typical differential geometry. The Laplacian term contains all the difficulties and the regularization associated with those trajectories. Another technical detail is this is not any Laplacian that I need, because there is somewhere I will need that the gradient of the Laplacian commute for geometrical reason, and this is the simplest one who do this. Okay, so suppose that you are in a very elementary case where the Legendre transform, classical one, is diffeomorphism. Then this guy, the solution of this equation, solve also this version of stochastic Hamiltonian equation. So you see reappear this strange term for P, because it's a covector, you have to be careful. This is still fixed. Otherwise, especially in the Euclidean case, this is just what you expect. Okay. Now, one of the good aspects, very good aspect of this second order strategy is that given a classical object, a classical Hamiltonian, you have explicit formula for the correction of geometrical origin or not. In my case, for example, for my elementary class of Hamiltonian, there is this expression, which is classical, plus a term here, which expresses this deformation, let's say, due to the irregularity of the past. This is not a wrong sign. Remember, we are Euclidean. Okay, the O in general is an additional second order variable which allows us to extend classical geometry to diffusion kind of trajectories. Another important aspect is that there are, in general, you have two additional variables in your Hamilton equations. One is this O, little o, and another one that we denote like this is associated, conjugated to little o, if you want. A very important point to understand, and we are going to consider section. Section in the sense that in this second order contingent bundle, the second order comes for this guy, everything is function of x, the process. So it's a kind of projection. It's a section on the configuration space. Okay?
Can I ask a question? Do the O's disappear in your connection nabla? In the second formula, there are no obvious O's anymore. I think they're now incorporated in the nabla, right?
Yes, you're right. We have computed this expression. You have computed this expression for the elementary class
right,
that I started.
The nabla is much more complicated than we usually want it to be.
Yeah. Okay. No, actually, this extra term will be absolutely fundamental. You will see why. So everything will be, in some sense, projected. It will be a section on the configuration space because the configuration will be the process. And everything, the process will contaminate all the rest in this geometry. Now, this least action principle has a value. What is the least possible value of the action when you do your your variational principle? Well, the good news is this is extremely simple. The function of the conditioned position and time can be written like this. Please, here, this is a bit of stochastic analysis, but not very important. This is called the Stratanovich integral. So it is a kind of regularized version of the Poincaré form. The Poincaré form, which is here. And therefore, here, there is the Hamiltonian with the deformation that I mentioned before. It is very important that this is not the classical Hamiltonian. This time I have expressed the boundary term, which is absolutely essential, which take into account the fact that we are on a finite time interval, and this corresponds to the value of S at the position, the final position of the process. The good news is that, look, log eta is S. This is a new version of the Schrödinger logarithmic transformation. The optimal drift is just essentially a gradient of the action, which is perfect. This is what we want. S solve an equation involving this term also for the Hamiltonian. This is, in this sense, a second order Hamilton-Jacobi equation because of this term. Of course, it is better known as Hamilton-Jacobi-Bellman. What is the good news? Eta solve this equation, which is an Euclidean version of the Schrödinger equation. Okay? Why positive? But you will see why. This is fundamental. We need positive solution to do the construction suggested by Schrödinger. As I said, there are two Hamilton-Jacobi-Bellman equations. So you could do the same, but with a conditioning in the future of your time interval. Then you will get, you remember there is a change of sign of the momentum. This is the Hamilton-Jacobi. You could call it backward if you want. It is a Cauchy problem, this one. You have the same logarithmic transformation of Schrödinger, and then you recuperate your more familiar heat equation because it has the right sign, okay? And this is a Cauchy problem. And here you have to tell me what is the initial condition for this one and final condition for the preceding one. So, but where do they come from, those two boundary conditions? It is strange. We need them to construct the process. Schrödinger had given already the solution in 31, which is strange. He understood that the joint probability of x of t, the process, if you take an initial Borel and a final one, should have this nice form. This is the integral kernel of the Hamiltonian you are considering. And those two guys are supposed to be positive in the past and in the future are the two boundary conditions you need. Okay, when the scalar potential is 0, h, little h is the Gaussian kernel, so it is continuous in all the variables, it is positive, it has all the properties you need. So, in general, if V is non-trivial, it means that since I need positivity of this guy, it is a condition on V. And there is a large class called after Qiao, which do this. So it's quite well defined. No, and this is the whole point, since you know the joint probability and you understand that this guy is evolved at any time, this one evolves back at any time t, you take 2 minutes to check that the probability inside the time interval is something very reminiscent of the Born interpretation of C. Okay? Because one solved the usual heat equation, though the backward heat equation. You could do this and you preserve this strange duality. Okay? There is another aspect. It seems that Schrödinger, when he designed his problem, thought that this was the only possibility to preserve what he wanted, to have a joint probability of this form. This was not true, in fact. There are many other possibilities, and the class of process involved is pretty large. But he was interested by this form, and in modern terms, this is just a Markovian process conditions, this product form. Okay, in fact, it is, in some sense, I called initially those process Bernstein because Bernstein was the first probabilist who read the paper of Schrödinger. Very few people read his paper, curiously. But Bernstein, a Russian probabilist, read it, and I found extraordinary inspiration in it because he said those processes are a stochastic counterpart of smooth trajectory characterized by the least action principle. In other words, he said there is a mechanics behind this. So this is the mechanic that we have here in some sense. And most of those processes are not Markovian. A key point which also excited me a lot initially when I tried to understand what Bernstein suggested, I recognized the one-dimensional quantum field definition. You see? So it could not be accidental, because in 1931 or 32, nobody would have thought about this. So, conclusion. You have a single diffusion which solves, curiously, two stochastic differential equations. One with respect to an increasing filtration. The drift in this elementary class is, in fact, a gradient of one of the Hamilton-Jacobi equation. The other is the gradient of the adjoint Hamilton-Jacobi equation. And D and D star are Ito differential. One, it is the usual case, this is the backward one. For those, I don't know if there is a true physicist in the room, a true theoretical physicist in the room, but if there is a paper of Parisi and Wu who got extremely successful, and which is called stochastic quantization. Naturally, Parisi was motivated by quantum field theory. But in the elementary case, finite dimensional case, this is exactly what you wrote formally, because everything is formal. He doesn't bother to show that the process exists. The only difference with Parisi is that we have two equations, because we have an information which comes from a joint probability. So it's also a good sign, because all the correcting gradients are here, even if it is a bit surrealistic. Recently, I saw a seminar of Gubinelli in Europe, who gave a lecture that you can find on YouTube, I guess, 2 hours lecture about stochastic quantization. Very interesting. At the end, he said, well, at the end, I still don't know what is stochastic quantization. What he meant is that it's completely formal, informal. Okay, but still the ingredients are correct, as always with good physicists. So. Now, the only problem left is to pick the boundary condition without which you cannot compute anything with your process. But this was also found by Schrödinger. Since we have a joint probability of the process which is critical for the dynamics, just take the marginal. And instead to think about a probabilistic Cauchy problem, think about a process, a method where you are given simultaneously an initial probability and a final one. Any, arbitrary. So the two marginal, you have this equation, which is not so trivial. It's an integral, it's a nonlinear equation with integral term, but it is written already in the paper of Schrödinger in the free case. He tried to prove that there is a solution. He could not make it. And the reason is that Berling in 1960, with hard analysis, proved that existence and uniqueness of positive solution. You need really positive solution. When you authorize one of the two probability to have a zero, you lose the uniqueness, but the existence is still valid. Now, everyone in this room understand why there is a strong relation with mass transportation, because in some sense, this is what Schrödinger was suggesting. And there is a book about this. The first one who connected the idea of Schrödinger with mass transportation is a Japanese probabilist. I will give you, he published a book about this with a reasonable summary of the situation today. He's a student of Fleming, the one of stochastic control theory. So I will give the reference at the end. Yeah. Now, the key point, the stochastic version of Jacobi integrability theorem. This is the first Hamilton-Jacobi equation that I consider for this elementary class of process. We are going to define a complete solution of Hamilton-Jacobi exactly like Jacobi. A complete solution, this is a family of solutions of this equation satisfying these same conditions. Family of solution, parameterized family of solution of Hamilton-Jacobi-Bellman. And for each possible value of the parameter, you have to solve this equation. So here is a theorem. Suppose that you give me a complete solution. And X will represent, let's say, a diffusion process with two parameters. Suppose that the process solved the first of our stochastic Hamiltonian equation. Okay? X appear here and here. And again, this is fixed. Here I'm Euclidean, I guess, probably. Yes, I'm Euclidean, so forget about this. It's just Euclidean. Then, the good news is that if you derive with respect to alpha, here, you get martingales. If you derive with respect to any of your collection of n parameters, you find a martingale of the critical process. Well, a martingale, this is not a number, but the expectation of a martingale is a number. But I will not need more. The second part is that suppose that you introduce another family of parameters associated with the martingale, and you say the expectation of this guy is beta. The second parameter, then you prove exactly in the same way, the same strategy that in the classical case, you prove that these two-parameter family of process with P is a gradient, as it should, are solution of our stochastic Hamiltonian equation. By construction, when h bar equals 0, you are back to the classical theorem of Jacobi, including the conditions imposed to make sure that it works. Okay. So in some sense, it's extremely easy to remember this theorem. It's essentially the same, except that when Jacobi is able, by derivation of his family of solutions, to find another family of constant, you do the same, but you get only martingale. But there is nothing better than a martingale to play the role of a first integral. Okay, some kind of conclusion. Hamilton-Jacobi-Bellman is only Euclidean. But it is really completely the quantum deformation of classical mechanical Hamilton-Jacobi equation. We have a stochastic least actual principle, which provide a class. I call them Bernstein again for personal reason, because he inspired me. But they are inhomogeneous. The drift depends explicitly on the time. So it was anticipated by Schrödinger that with this, he didn't have the notion of diffusion process at the time, but the key point that the family was time reversible, which is pretty bizarre. This is a problem of classical statistical physics. Forget all the rest. You give two probability density, you fix an Hamiltonian, whatever is the name. This is classical statistical physics. The drift depends on the time, and still the processes are time reversible. Most of physicists believe that it doesn't make sense. So the key point, maybe, is that the concept of complete integrability of the classical Hamilton-Jacobi equation goes straight forward to Hamilton-Jacobi-Bellman, with the only detail that the half of the constant involved are not really constant, but are martingale. Their expectation is a constant, okay? And the good point, of course, this is why I choose this class of process, which have a classical counterpart. When h bar is 0, you are reduced to the classical theorem of Jacobi and the condition that he imposed to solve Hamilton equations. So, a word on the reference. The first one, there are two versions of this paper. The first one is in German, and although I'm Swiss, I'm not too good in German. So I read this one, which was some kind of French translation published in Annales Poincaré 1 year after, the original in 31. And quite frankly, I understood after why nobody had read this paper, because this is why I wrote here last section. It is only the last 5 pages of a 30 or 40 page long paper which are devoted to this strange problem. Okay? The second one is a long paper where you will find most of what I said expressed in a geometrical way. Qiao was a young postdoc in Lisbon a few years ago. And he is the one who came with the idea of second order stochastic geometry. Well, I didn't know. I've learned this with Ito calculus. But in this context, quite frankly, it is second order idea, the idea to go on to develop a calculus when you have to take into consideration extra second order term. It's very natural, very appropriate to stochastic analysis. This is the little book I was mentioning. He's a student, ex-student of Fleming. He called this stochastic optimal transformation control with fixed marginals. It is very recent. And finally, I will recommend this for those who have some inclination for geometry, because I try to go to the original paper of Meyer and Schwarz. Manifestly, a lot of ideas were coming from Schwarz. There is a little review by Schwarz of this book in the Bulletin of the AMS. Good luck. Try to read it. Personally, I confess that it was so abstract that I could not really do. But this one This is very detailed, very elaborate, very elementary, full of example. I recommend this. Okay, this is in this sense that we owe to Emery part of what we do here. Okay, great.